All right, hello class. This is Dr. Cooper. We're starting chapter 15, which is covering conjugated systems. Okay, so very quickly for our overview of this lecture, we'll first start discussing conjugation and conjugated systems. All right, this will lead us into a discussion of this new foul stability, and this is really just typically resonance stability now. Okay, there's a new chemistry that comes out of conjugated systems. We're going to be covering this conjugate addition, also known as the 1,4 addition. All right, with 1,4 additions now being a part of our conversations, we need to learn selectivity. How can we garner selectivity for the 1,2 or the 1,4 product to conjugated carbonyl containing molecules? Okay, and there's two ways that we can control those type of chemistries. We'll talk about that. All right. Also, we'll cover nomenclature of dienes and trienes. And with that, there's some new chemistry that's very specific to dienes, this Diels-Alder reaction. All right, so this is a very important reaction to talk about. So Diels-Alder reactions are these pericyclic reactions. They form 6-member rings and then also referred to as 4+2 cyclic additions. All right, so I need to consider which reagent is a diene or a dienophile. Okay, if I react with cyclic dienophiles, I get fused ring systems and Diels-Alder reactions. But cyclic dienes give bicyclic rings. Stereochemistry is important, so I need to learn the endo rule selectivity here. And I need to learn chemistry of unsymmetric dienes, all right? So we'll learn which diene yields the 1,2 as the major product or the 1,4 as the major product, okay? Very briefly, we'll cover UV-Vis spectroscopy. And our segue into chapter 16 is this additional level of stability. If my molecule is planar and it has a conjugated cyclic array of an odd number of pi bonds, this new stability that we gain is referred to as aromaticity. So let's cover conjugation really quickly. All right, these are organic materials with alternating pi bonds. All right, so pi or alternating pi bonds have to have a scenario where there's a double bond, single or double bond, or a triple, single, triple, or even a triple bond, single, double bond type of scenario. Alternating has to afford a single bond in between those two pi bonds. Okay, so for a check of this, can you guys describe below or choose below which molecule is conjugated? All right, so there's 4 molecules here, A, B, C, and D. Can you guys tell me which molecule is conjugated? I'll give you guys a few seconds here. All right, hopefully you guys had enough time. Let's take a look at molecule A really quickly. I see a double bond. I'm going to use 2 lines to describe that. I see a single bond, another double bond, a single, a double bond, and another single, right? So this case appears to be conjugated because I have single, double, single, and double, all right? And that fits our definition of conjugation, which is a molecule that has these alternating pi bonds. And again, that could be double, single, double, like we have in this case here. Let's take a look at molecule B. Again, I'm going to start here with a double bond. I see a single bond. I see another double bond there. A single bond, double bond, single, double bond, single, double bond, another single, another double bond, and another single bond, all right? I can continue this on with the rest of this molecule, and I will see that this molecule also has that alternating double single scenario. So molecule B also appears to be conjugated. Let's take a look at molecule C. I'm going to start up top here with this triple bond. Use 3 lines to describe that. I got a single bond here, another single bond, and then a double bond, all right? So C appears to be a little different, right? I don't have a separation between our 2 pi bonds by 1 single bond. Instead, there's 2 single bonds, all right? And in this case here, C does not have alternating bonds, all right? The 2 singles are not alternating. Let's take a look at D. I'm going to start with the pi bond between this oxygen, this carbonyl. I'm going to say there's 2 here because it's a double bond there. Again, I have a single bond, another single bond, then this double bond, all right? And in this case here, it also does not look conjugated, all right? So molecules C and D, if you guys give me a second, I'll erase this. Okay. C and D are not conjugated, all right? Instead, we consider these pi bonds as being isolated, all right? Because they're not alternating, there's a couple of single bonds in between, so they're isolated from one another, okay? So the answer to this question, which molecules below are conjugated, is actually molecules A and B. All right, conjugated systems are more stable than non-conjugated ones. Let's see if we can make some sense of this. If you take a look at this diagram, and if we look at this diene, the 2 pi bonds and our carbon-carbon double bonds have a small overlap right where the single bond meets, and that's between carbons 2 and 3. This overlap allows the 2 pi systems to extend its delocalization now over all 4 carbons. And whenever I can delocalize electrons, I'm actually stabilizing the systems. So conjugated systems are more stable due to this electron delocalization stability attribute. So now I can start to study the relative stabilities of these pi systems, or multiple pi systems if you want to as well. So accumulated diene, this is a diene that has the 2 pi bonds attached to the same carbon. There's no single bond in between. This system is extremely unstable, all right? Whenever the 2 pi bonds are attached to the same carbon, 1 pi bond has to be 90 degrees to the opposite pi bond, all right? That forces the 2 pi systems not to overlap at all right? And there's no stability that is gained. Instead, those pi electron clouds possibly prefer not to be 90 degrees from one another either, all right? So that builds up a little bit of instability in the system. But if you skip over to the conjugated diene, all right, if you look at the diagram here, it's the lowest energy structure corresponding to being the most stable, all right? Those 2 pi bonds can effectively overlap and allow delocalization. If I take a look at the terminal alkyne, it's higher in energy than the N-terminal alkyne. We know that increasing the substitution patterns will allow pi systems to be more stable. All right, and that is the same effect for these 2 isolated dienes. Trans-hexa-1,4-diene has a mono and a di substituted, while penta-1,4-diene has only 2 mono. So the mono-di system is going to be more stable than just the 2 mono substituted alkenes. Okay, let's cover nomenclature of dienes and trienes. This molecule here has 2 alkenes, so we're going to specify it as a diene in its name. All right, it's a total of 5 carbons if we start carbon 1 at the pi bond. We're going to start carbon 1 at the pi. This allows us to have the lowest possible numbering. And then we need to make sure that we specify any unique orientations across our double bonds. All right, don't forget that we have to use E and Z to specify the stereochemistry there. Okay, and alkene 3 and 4 have a unique orientation that is trans, so it's going to get the letter E. So name this molecule here is E-penta-1,3-diene. If I want to name this molecule, I still have 5 carbons. I'm going to start my 1 at the double bond again. This gives me dienes or a double bond at carbons 1 and 4. So the name of this molecule will be simply penta 1,4-diene. All right, there's no cis-trans orientation across the double bonds here. But looking at this molecule now, all right, this is a alkene or a diene that's locked into a ring. Again, we're going to start 1 at a pi system. I'm going to stop at 4. However, we know there's a total of 6 carbons here. So the name of this molecule will be cyclohexa 1,3-diene. If I want to name this molecule, now I have 3 double bonds. All right, so we're going to use the word triene here. I'm going to start 1 again at a pi bond and number that accordingly to where I have the lowest possible numbering for all alkenes. The name of this molecule will be cyclohepta 1,3,5-triene. So really shortly here, for your practicing needs, can you name these 2 molecules? All right, they're a little tricky, but at this point, I think you guys can do it. I'll give you a few seconds to try. Okay, hopefully that was enough time to practice naming these. Let's take a look at the first molecule on the left. All right, I want to find the longest continuous chain or the longest alkyl chain. I want to properly number that chain to where I give substituents the lowest numbering. And then I want to deal with identifying substituents or dealing with those correctly. And then I want to piece all that together to come up with a proper name for this molecule. All right, so the longest continuous chain should have 11 carbons, and I'm going to number my chain this way to give my substituents the lowest possible numbering. All right, you want to try and compare this to the other numbering to see why this numbering gave the lowest possible numbering, if that's a avenue or area you need to practice. Okay, let's also identify all remaining carbons that are not part of the parent chain. Okay, so these 3 systems here need to be identified in the name. All right, And then also uniquely at carbon 8, there's a wedge there indicating stereochemistry. So I need to go ahead as well as identify this stereocenter, all right? So I went ahead and label or number the priorities for the groups there, and that stereocenter is assigned an S. All right, so if I piece all this together, I should come up with a name that is 8S 7-sec-butyl 2,9-dimethyl deca 3,5-diene-8-all. Okay. I will have virtual office hours this week, so please, if there's some questions that you might have with this naming of this molecule, let me know. If I take a look at the second molecule, all right, hopefully this should be a little bit easier. All right, my longest chain is 5 here, right? I have to include both carbons of the pi bond in the system here, okay? So it's going to give me 5 in this direction. So that means that everything that's not part of the parent chain will be a substituent. All right, so I have those identified. And, all right, I need to also specify any unique stereochemistry, okay? Carbons 2, all right, or the pi bond between 2 and 3, we have to indicate what type of stereochemistry is there, and hopefully you guys can see that there's a trans orientation there. All right, so this is going to be 2E 2-cyclopropyl, okay, 3-alpha 4-methyl penta 2,4-diene. Okay, so now that I can determine if a molecule is conjugated, let's consider the conjugate addition, also referred to as a 1,4 addition. Let's take a look at this diene, all right? There's 2 carbon-carbon double bonds in this structure, also known as 2 alkenes. So if I have 2 of those, I'll use the word diene to describe the system, all right? Let's see, or let's keep track of all atoms that are in conjugation here. So 1 and 2 of this first double bond, and we realize that atoms 3 and 4 are also conjugated to that, all right? So in this system, there's 4 atoms that are conjugated, 1, 2, 3, and 4, are these 4 carbons. Now let's see what happens if I have a nucleophile undergo a conjugate addition to this system, okay? So I'm going to attack carbon 1, and the electrons in the pi bond between 1 and 2 will move now between atoms 2 and 3, and the pi bond between atoms or carbons 3 and 4 will leave a lone pair on carbon 4. All right, so we were learning here that the conjugate addition involves all atoms in the conjugated system. So carbons 1 through 4 have to be involved now in a conjugate addition. That leads to this intermediate here where carbon 1 has a bond to the nucleophile and carbon 4 has gained a lone pair in the form of minus charge, which is referred to as a carbanion. I can take this same diene system that has the atoms, or that has the carbons, 1 through 4 conjugated, and this time I can react it with electrophile. All right, the reaction arrows are moving in the opposite direction now because the pi electrons in the diene are the nucleophile and the electrophile are seeking electrons. Okay, so E plus is referring to an electrophile that's needing electrons. Okay, so now the electrons in the pi bond between atoms 4 and 3 are moving down to atoms 3 and 2, and the pi electrons in atoms 1 and 2 are making a bond with the electrophile. All right, so that leads to this new system that has a new bond between the electrophile and carbon 1, and carbon 4 now has a carbon cation. All right, so in the conjugate addition, I see now why this is referred to also the 1,4 addition, because carbons 1 and 4 are the reacting carbons, or the carbons that are undergoing some type of change. Okay, in both systems, I made a new bond with carbon 1, and carbon 4 is set up in these systems now to also make an additional bond. Okay, so how do we induce these conjugate additions? There's 2 ways. The first is with the proper reagent. The organic cuprate, also referred to as the Gilman reagent, is the reagent, or is the nucleophilic reagent that undergoes 1,4 additions. Okay, And the opposite way, or the other way to induce a conjugate addition, is with a thermodynamic reaction condition. And thermodynamic conditions are heated or prolonged reaction conditions. All right. A thermodynamic product is usually the most stable product, and the conjugate addition will lead to the most stable product. So if you heat a reaction long enough, or allow it to react long enough, you will induce the 1,4 addition or the conjugate addition, because it would need to afford the more stable product. All right, so now there's reaction selectivity that I have to explore. I can either have the 1,2 or the 1,4 products. So how can I know which conditions are going to favor which type of product? All right, so let's look at reaction temperature first. If I take this diene, I'm going to label the carbons 1, 2, 3, and 4, and I'm going to react it with HBr, which is an electrophile. Okay, my two temperatures are going to be either cold or warm, right? So if I do a negative 10 degrees Celsius reaction, all right, this is known as the kinetic conditions. All right, and this is going to be favoring the fastest product that can form. In this case here, that's going to be the 1,2 product. However, we described this before. If I heat the conditions, we're going to heat this at about 80 degrees. This is known as the thermodynamic conditions, and this is going to favor the 1,4. All right. So temperature has a really nice way to garner selectivity. Heating it, I would get the thermodynamic product, which is the 1,4 product. But if I cool the reaction's temperatures down, I'm just going to favor the kinetic, and that will lead to the 1,2 product. All right. Let's take a little closely, a better look at these products really quickly. The 1,2 product has the least substituted alkene. It's a mono-substituted alkene. All right, I hope you guys can realize that. If you look at the double bond there, and there's only one carbon attached, this is the fastest possible product that can form. However, the 1,4 product is the most stable alkene. It's di-substituted here. All right, you guys can realize there's 2 carbon groups hanging off that double bond. All right, so this is the most stable product. It's highly favored. Okay, so let's look at the mechanism. Let's see if we can make some sense of this there. If I take my diene, it's going to extract the proton for HBr, and the HBr bond is going to break, giving electrons to bromine. That's going to generate this carbon cation, which is the secondary carbon cation, and the bromide ion. All right, a Br minus. This Br minus can react with the carbon cation, and if it does, it leads to the 1,2 product. All right, this 1,2 product is not stable. If you look in between here, there's an equilibrium arrow here. All right, I'm gonna circle that really quickly. All right, so it's letting you know that this product can equilibrate back to this carbon cation. So it can, the bromine can fall off again, and now you generate back your secondary carbon cation. But this compound now undergoes resonance delocalization to generate the primary carbon cation, and now our Br minus can react with that carbon cation, which is primary, is unstable, but it leads to a more stable product, so this is still a favorable process, and that leads to the 1,4 product, right? Now let's consider reactions to conjugated carbonyls. Let's say I want to react this conjugated ketone with various organometallic reagents. First, let's find the 4 atoms of our conjugated system. In this case here, we will start atom 1 at oxygen. Atom 2 would be the carbon of the carbonyl, and atoms 3 and 4 are now the carbons of our alkene, all right, or our carbon-carbon double bond. Let's see what happens when we react with our organometallic reagents. First, let's look at a Grignard. Reacting this conjugated ketone with vinyl Grignard gives the 1,2 product as the major. If I use an organolithium, in this case vinyl lithium, I also get the 1,2 product as the major. You guys just learned, if I take the cuprate and react with this conjugated ketone, now my major product is the 1,4 product. All right, I get this important intermediate out, which is called an enolate. This gets protonated to this final product of a ketone. Okay, What's important here, again, is that the cuprate yields the 1,4 product as the major product. Let's consider this reaction's mechanism really quickly. Okay? So the R group in our cuprate is going to attack carbon 4 of our conjugated system. The electrons in the pi bond between atoms 4 and 3 are going to break now and move to make a pi bond between atoms 2 and 3. And the pi bond in between atoms 2 and 1 would break and leave electrons only on atom 1. All right? So this gives us this intermediate. Again, there's a pi bond in between atoms 2 and 3. Atom 1, which is the oxygen atom, gain a lone pair. Now it has a formal minus charge. All right? This intermediate is known as an enolate. And enolates are usually very reactive with water or protonated systems. Hydronium, protonated water. All right? So this enolate is going to be protonated. The electrons in the oxygen, okay, or electrons on oxygen, are going to reform a carbon-oxygen double bond, all right, and the pi bond in between 2 and 3 are going to break to pick up or to be protonated, all right. So there's going to be an H that's get protonated from H3O, or hydronium ion, all right, and that bond is going to break and put lone pairs back on oxygen, all right. So I get this final product is a ketone. That H in red is typically not drawn, but I just wanted to keep track of where did I gain that extra H, and it came from the protonated water species. Okay, so there's really two steps to this mechanism. All right, you have this nucleophilic attack, and then you have the protonation of the enolate. All right, you guys are responsible for this mechanism, so please take care to study this closely. Okay, here are some problems to practice. I'll give you guys a few seconds to try these. Okay, if you need more time, please pause the video. Structure 1 has a diene that's being introduced to HBr under heat. All right, these are thermodynamic conditions. This is going to favor the 1,4 product, and this is going to be the major product. All right, if you need to, please investigate the other potential product and just try to convince yourself to why this would be the major product for this first structure. There's a small trick here. All right, question 2. I have this conjugated ketone, and I have this organic cuprate. The major product here should be this, where I add a methyl group on carbon 4. All right, the enolate intermediate gets protonated to regenerate the carbonyl of the ketone. All right, structure 3 is just a basic elimination. Okay. All right, the question should be, where did I pull an H? Did I pull the H next to the pi bond or the methyl side? Okay. In this case here, you guys should realize that not only pulling from the side that has the fewest hydrogens, which is zeta rule, okay, but also I get a conjugated diene as well. All right, so this is just a mental note that if you can form conjugated materials, you will. All right, those compounds are going to be more stable. And lastly, I have this cuprate with this conjugated ketone alcohol substrate. And here I would get no reaction. All right, this is just a recap of remembering that organic cuprates, organic metallic reagents as a whole, are not compatible with protic H's. All right, so the OH bond will quench the cuprate. Instead of getting the Michael addition, I get just a deprotonation, and then the second step, which is adding the hydronium cation, will protonate back the alcohol to generate the starting material. All right, so I get no new products, so this is just no reaction.